All right, so let's do 12,155 here. And I think the most difficult part about this problem is the coordinate system that we're using here. We're given that a particle is moving in a circular path. So it's orbiting around with a radius of 4 inches. And we are given this equation, theta equals cosine 2t. So if we put in t in seconds, we get the position or the angle of it, theta. So the coordinate system that we're going to use here is we have a component in the radial direction, which is pointed directly out from the radius, and then one in the transverse direction here, which is denoted by theta. Okay, so I think the tricky part about this is where do these equations come from? And if you're not interested in where the equations come from, you can skip ahead in this video. But I'm going to go through a little bit where the equations come from. So we're given the velocity vector in this system here, where the velocity vector is r dot in the radial direction, and then we're also given r theta dot in the transverse direction. All right. So what does this mean? Well, in the radial direction, it's r dot. It's just the time rate of change of how that radius is either expanding or contracting. In the transverse direction, right, if we're looking for the velocity in kind of this tangential direction, if you want to think of it that way, we would get that by taking r times the angular velocity here, which is theta dot, right? So if theta dot is in radians per second, we multiply that by r, and we would get the velocity in the transverse direction there. Okay, so in the acceleration, this is where the trickiness comes in, is we need to take the derivative of the velocity. Well, how do we do that, let's say, for this first component, r dot times the unit vector in the r direction? Well, we need to take the derivative of the first, which is r double dot, times the second, which is the unit vector in the r direction, plus the first times the derivative of the second, ur dot. Now, what is this unit vector dot rate of change of the unit vector? Let's just keep it that way, and I'll explain a little more in a second. Okay, so then to add on there, we need to do the same thing for the second term here, which then comes out to derivative of the first, r dot, times the second, which is theta dot u theta. And then we need to take the first, which is just r, times the derivative of the second. But there are two terms here, so we need to be careful about this. So we get theta double dot, that's the derivative of here, times the second, plus the first, which is theta dot. Make sure I get those double dots on there. Theta dot times the derivative of the second, which is u theta dot. Okay. So the difficult part is knowing what these terms are. When the unit vector, we're looking for the derivative of the unit vector. And this term over here, which we have u theta dot. All right. Now, the book derives this on page 72 and 73, but I'm not going to go into that. It gets too far in the weeds, and you're probably just looking for the answer anyway. So let's go through here. So what ur dot comes out to be is nothing more than theta dot times u theta. All right. Likewise, u theta dot comes out to be, make sure I get this correct here, that comes out to be negative theta dot times ur. Okay? All right, the book explains this, but we can just sub that in. So we get this acceleration equation here, which comes out to be, in the radial direction, we have r double dot minus r theta dot squared. And that's the term in the radial direction, so we multiply that by the unit vector in the radial direction. And then we have the transverse direction, which comes out to be r theta double dot plus 2r dot theta dot. All right, and let's make sure the unit vector is there in the transverse direction. So this is the solution of the acceleration vector. So with our problem that we're given here, we're given the radius r is 4 inches. And that doesn't change with time. It's moving in a circle. So if it's not moving, it's not getting bigger or smaller, r dot is equal to 0, and r double dot is also equal to 0. So anytime we see those terms in our equation here, we can set those equal to 0. So 0 here and 0 there. All right. Now let's look at how do we get theta dot and theta double dot. Well, we know theta is the cosine of 2t. All right. And if we take the derivative of that, we have theta dot is equal to negative sine 2t. And then we need to make sure we're taking the derivative of the inside there times 2. So this comes out to be negative 2 sine 2t. All right. All right. So we have this theta dot, but what do we put in for t? We don't know t. Well, how do we solve for t? Well, what we're looking for is the magnitude of the acceleration when theta is equal to 30 degrees, or when that's pi over 6 radians, the same thing. So if we make sure our calculator's in radians, we put pi over 6 in for theta, and we solve for t, we come out, t is, let's see, 0.5099 seconds. So when t equals 0.5099 seconds, theta is 30. So since we're looking for the acceleration at that point, we put in that value here for t. All right. So theta dot comes out to be, do I have that value? Yeah. Theta dot comes out to be negative 1.7039 radians per second. And then we do the same for theta double dot. Theta double dot, we then take the derivative of this equation here, and that comes out to be, looks like negative 4 cosine 2t. And we then again sub in this 0.5099 for t, and that comes out to be negative 2.0944 radians per second squared. All right, so now we have these values, and I think we're able to sub those into each one of these, right? There's no value missing. So we get the radial component and the transverse component. So the radial component on this side comes out to be, looks like negative 11.6135, and that's inches per second. And the transverse component comes out to be negative 8.3776 inches per second squared. Sorry, inches per second squared here. Got the units incorrect. All right, now just to find the magnitude, then we take the sum of the squares and then take the square root of that. So we have our magnitude is equal to, let's make this a magnitude, is equal to AR squared plus A theta squared. And that value comes out to 14.3 inches per second squared. All right, and that is our answer for 12.155.